So I want to talk about the prime number theorem in arithmetic progression. Okay. So you have seen the prime number theorem already. The first week was devoted to first 4 days were devoted to this topic, prime number theorem. So what's going to happen now is that we are going to have the primes are not going to be all primes, but they're going to be primes which will depend on a modulus condition. So that then now you can guess that the zeta function will be replaced by an L function. And this is a nice, of course, in itself, a very nice area to study, but it's also nice because we have just looked at the zero-free region. Yesterday, we studied the zero-free region, and we studied everything that we have studied till now is going to find an application in the proof of this theorem. And it apparently looks quite simple. It's not all that simple. Yeah, it's not all that simple. And so intuitively, where do you think the difficulty is going to come from? Depending on what we know till now. Where do you expect a difficulty here? What is new? What is new between, so what you're trying to find is the number of primes. Oh, এটা কি কোনো জরুরি কিছু লাগিয়ে নেব where is the difficulty, where do you expect, what is different? I mean, something that we studied yesterday, it's the existence of a possible zero, the Siegel zero. That's what makes getting uniform results difficult in the case of the prime number theorem and arithmetic progression. So it's a nice application of the things that we saw till now. Okay. So yes, so we will use some notations. You know them all. I mean, you don't know them all, but you can guess them all. So you saw that our aim for the prime number theorem, the classical prime, the usual prime number theorem, is to find the number of integers that are less than a certain bound, yeah, to find some results for that. The first thing is, of course, very simple, that there are infinitely many primes that we know. And then, so the similar thing here we have seen, there are infinitely, in the first day, on Monday we saw this, that there are infinitely many primes in arithmetic progression. And now we want a qualitative result to show this. So let us take we will take the notations that we will use are the notations that are parallel to the prime number theorem without arithmetic progression. And so this is pi x q a. Okay, the new thing here is the q. So this is the number of primes which are less than x, but not all primes, but these primes are congruent to a modulo q. All right. The other thing, the smooth version of this is going to be psi x q a, and this is going to be defined as all primes which are less than, so this time we are going to have lambda of n okay, n less than equal to x and n congruent to a modulo q. All right. Lambda is the von Mongol function. Yeah. You remember this? Lambda of n is equal to log p if n is a power of a p, prime power p, and it's 0 otherwise. So use of this makes life simpler because this is smoother, and then by partial integration, you can get back the pi. Okay. And so we will take, as usual, we will take L of okay, and we'll just I will write that a bit later. L will simply be a Dirichlet function with modulus q. Okay, so the case q is equal to 1 is the Riemann zeta function. All right. So yeah, A and Q should be co-prime. So I want to recall things that you already know. So if A and Q are co-prime, this condition is to make the definitions consistent. So we always have this A and Q to be co-prime. And then we get a, you know how we get a linear combination of characters. So these are just, I'm just writing them out, though we have seen them before. So we get this. If I take the sum of chi bar A and chi of n, take the sum over chi, and I normalize by the Euler-Phi function, then this, you know, you remember this? It is either 1 or 0. So it is 1 if we have n from the congruent class, n is congruent to A. And otherwise, so now if I multiply this, if you multiply this by lambda of n, okay, the von Mongol function, then, and then we take the sum, what we are going to get is psi x q a in terms of this. So multiplying by lambda n and summing, what we get is, take the sum over chi, same thing, chi bar of A and then we write psi of x chi divided by phi of q, and this is equal to psi x q a. So yeah, yeah, you remember what psi is. So the notation is clear now. We can remove it. You remember this, psi? So psi of x chi, this is sum of chi n lambda of n, where n is less than or equal to x. So this is the equivalent of the psi of x that we have for psi of little x that we have for the prime number theorem. Okay. So now we will use, what we will use is an explicit formula for psi x chi. Okay. So we use an explicit formula, and much of our effort will be in obtaining such an explicit formula for psi x chi. Okay. So because if you have psi x chi, then you can use that to get psi x q a, all right, by this result. So the theorem that we propose to prove is an explicit formula, and let me write it out. So first let me write it, and then I will tell you what is. So here is our theorem. It says that psi x chi, this is equal to E0 chi into x. You remember E0 chi, we've used it before. It's either 1 or 0, depending on whether chi is chi 0 or not. And then an error term. And what does this error term look like? This error term is big O of x exponential minus C1 square root of log x. Okay. This is the result when there is no exceptional zero. And when there is an exceptional zero, we get this to be equal to minus x beta 1 by beta 1. The exceptional zero is called beta 1 often, plus the same error. The exceptional zero is the zero we saw yesterday. I mean, we didn't see it. We don't know if it exists. So we said that it might exist. Nobody has seen an exceptional zero yet. So nobody really wants to see it. We don't want an exceptional zero, but we don't know how to get rid of this. Okay? And so what's wait, this is not, you didn't stop me. such a wonderful result cannot exist, right? So this depends on the Q here. If so, Q is less than equal to exponential 2 times C1, the 2 is not particularly exciting, square root of log x. Okay? And E0, so that's the bad one. You see, it's this bounds that are, in such results, it's these things that are not good. And these things that we don't know how to really make very good. Okay? So there's one thing that is not yet, yeah, it is, but which I should say, E0x, E0 chi, this is either 1 or 0, depending on whether chi is equal to chi 0 or not. Okay? Okay. So now we will prove this explicit result. So you remember, and this we did in the last classes, that maybe 2 days ago. So I'll keep the theorem over there, and so if we have an explicit result, explicit formula for psi x chi, from here we can get the prime number theorem, or the form of with psi x q a, from which getting the prime number theorem is a trivial affair. So let us concentrate on this. Okay. So the proof. Do you have any questions? So how does the proof go? So you remember that use this. If I take L prime by L, okay, of S chi, then this is equal to the summation of lambda n pi n by log n and n to the power s for n going from 2 to infinity, and sigma greater than 1. That's not true. No, if I take L prime by n, then there is no, this is if I write simply L prime. So chi n, there's no log here anymore, and I can go all the way down, n to the power s. This you remember. We did this, yeah? And we use this to write psi x chi, okay? Psi x chi this is equal to, so this is minus 2 pi I, the integral from sigma 0 minus it, sigma 0 plus it, L prime by L S chi x bar S by S plus a certain error R for sigma 0, which is greater than 1. This is a standard technique. You remember this. And so what I will try to do is, I will have a rectangle, and as you do in the prime number theorem, which you have seen the proof, okay. So as in the proof of prime number theorem, what we do is we take t to be at least 2 and to be less than x, and we take the sigma 0 to be equal to 1 greater than 1, remember? So something like a small thing, 1 plus log x. Okay? And this r that I have written here, this r is bounded by x by t log square of x. Okay? So as in the prime number theorem, we take a closed contour which contains of 4 points. You know which 4 points it's going to take? We're going to get a rectangle, and this, and then which 4 points are you going to take as in the prime number theorem? So you already can see 2 of them, sigma 0 plus it, sigma 0 minus it, and then I need 2 more, which I will choose. I'll take something. So the choosing, of course, I will choose, but the choice is not something easy. Why? Why is the choice not easy? Can you somehow? I want to contour. What should I expect within this contour? I'm going to take an integral here. Okay. So what should happen? What should happen in this is that the exceptional 0. So I have to be able to manipulate my exceptional 0. Okay, I have to choose the points in such a way that I still have some control over that. Okay, so use a closed contour. Let me call it C. Okay, which joins these 2 points, these 4 points. So it's over there sigma 0 minus it. So there is a t. There is a t up here somewhere, t minus t here, sigma 0 and minus sigma 0. Yeah? So, so sigma 0 minus it, sigma 0 plus it, and then I will have 2 more points, sigma 1 plus it and sigma 1 minus it. Okay, so what do we have to do? The importance is to choose the sigma 1. So it is important to choose sigma 1. this sigma 1, yeah? We choose sigma 1, and what should sigma 1 do? Sigma 1 such that the contour does not pass close to 0. Close to the exceptional 0. So by close, when I say close, I can use the results that I know, the results that we have talked about yesterday, that where can the exceptional 0 not be? All right, where can it not be? So now we are going to do a case-by-case work on this theorem. Okay, so theorem. So that's you remember our theorem. And so first case is the easy case. So what is the easy case according to you? What is the easy case? Tell me. This time you're going to break depending on the 0, not on the chi. So which is the easy case? Where can it work like the prime number, classical prime number theorem? When there is no exceptional 0. Yeah? When there is no exceptional 0, we are in the old case of the similar case as. So we'll do that first. All right. So case 1. So there'll be 3 cases. So case 1, when there is no exceptional 0. Case 2, when there is exceptional 0. So what is case 3? Case 3 is case 2 broken up into 2 parts, when the exceptional 0 will be close and when the exceptional 0 will be firm. Okay, these are the 3 cases that we will look at. So that's when I promised you that we are going to use exceptional 0, I'm keeping up my promise that we are going to use them. Yeah. So it was not just for fun that we introduced them. I mean, maybe someday exceptional zeros will be just for fun. I mean, it'll be proved that they don't exist, and in that case, all these proofs will become very simple because there will be no case of. So the case 1 is there is no exceptional 0. All right. So now, what did I tell you? I told you that we will choose it. We will choose sigma 1. Yeah. So let me choose sigma 1 to be equal to 1 minus C upon log qt to the power some alpha. Okay. Where what is the C? This C is the constant. Does this speak to you? This kind of a result, 1 minus C upon something? This is the zero free region, yeah? C is the constant. In the zero free region. So what is the zero free region? Which we studied this yesterday, that there exists a constant such that beta is less than 1 minus C upon log qt. all right? Now, either chi is non-principal or chi is principal. So suppose chi is non-principal, what happens? Where is my integrand? Okay, it's not on the board anymore, but remember what it was. It was the integral of L prime by L, L prime by L, x bar s by s. Okay, and we are on this contour. So what happens when chi is non-principal? If chi is non-principal, what happens? Who is not feeling sleepy? Yeah? Is this analytic? Yeah. If it is non-principal, it is analytic. There's no problem. Yeah. Problem would be when chi will be chi 0. Yeah. So either chi is principal or chi is not. So begin by chi being non-principal, and then what we have is, then the integrand is analytic. Okay, in C. C is my concept of integration. If not, chi is equal to chi 0 if chi is actually equal to chi 0, what happens? If chi is equal to chi 0, I have L prime by L. What happens? Is there a pole? Yes, S is equal to 1, there is a pole. Yeah. So there is a pole. At S equal to 1. We know this. And the residue is X. Okay. Then what we had minus, which is no longer on the board, but I had an integrand there, minus 1 by 2 pi I, and I'm taking this integrand over C, L prime S chi over L S chi, x bar S by S. This is now equal to E0 x x. All right? So the explicit formula now can be written as psi x chi is equal to, I have E0 x, E0 chi, sorry, E0 chi x, and no, let's remove this the main term. This is going to be less than x log x square 1 by t plus exponential minus c log x, and that alpha which I took here, okay, by alpha log qt. So Yeah, so this is when I have the case 1, there is no exceptional 0. So the second case now will be when exceptional 0 exists. So this is my case 2. Case 2 is when exceptional 0 exists, exceptional 0 is Visible 0. Yeah. So there is an exception. I'm allowed to write an exceptional 0 because I know that if it exists, there is only one. Yeah. I mean, it's already bad enough. We don't want many of them. One is already, there is an exceptional 0, which I call beta 1. And as I told you, there are, what we have to take care is, where is beta 1? Okay. So if beta 1 is greater than or equal to 1 minus c upon something which is not necessarily the same c, some same alpha, but some kind of an alpha 1 log qt. Okay. Now what happens here? What happens here? If beta 1 is greater than or equal to 1 minus some constant times alpha 1 log qt, that means I will get, by suitable choice of sigma 1, I'm going to get a 0, a pole in the contour. All right. So I will choose sigma 1. This time, how would you like to choose sigma 1? The first case, I had chosen sigma 1 minus c log qt by alpha. Okay. So that means 1 minus c, if I take it, I should take now something which is smaller than alpha. Yeah. In fact, even smaller than this alpha 1. So we choose sigma, which is 1 minus, so that the same c, some alpha 2 log qt. Okay. And alpha 2 is less than alpha 1, which is less than alpha. All right. So what will happen now? Can you guess? What's going to happen now inside the contour? Yeah. This, you know the zero free region. Yeah. So beta 1 is greater than 1 minus c. So I get a pole. Now we get a pole where? Inside, but at beta 1. My exceptional 0 is at beta 1. Okay. Now there is a pole inside C, inside my contour, and beta 1. Okay. So this gives what I want, x to the power minus x to the power beta 1 by beta 1. All right. So now put it all together, and this case 2 will be, so psi x chi, I aim, don't forget what we wanted to do. What we wanted to do was to get psi x chi. So this is our case 2 is going on now. So there is this pole. So the explicit formula in this case is psi x chi equal to, so this one will come back, minus x by beta 1 by beta 1, and then another term, big O of x log square x times 1 by t plus this inside your integral x, maybe we can remove this. Mm. 1 by t plus, like before, the exponential of minus c log of x alpha log t. Okay. Do I have the good number of brackets? 2, 3. Okay. So that's okay. So what's case 3 going to be? Who will help me? You have case 1 here, case 2 there. So case 3 is? What remains? What remains? What remains? You're a fan of Pink Floyd? No. What would you study in case 3? So what is not? Case 1 has been done. There is no exceptional 0. Case 2 has been done. There is an exceptional 0 which satisfies this condition. So what should case 3 do? It should be the complement of this. And what is the complement of this? You change the sign. Beta 1, there is still an exceptional 0. This is a subcase of exceptional 0. And the rest of the cases is the complement of this, which is beta 1 this time is, it should be, the complement of this will become less than, yeah? So case 3 will be, there is an exceptional 0. So case 3 is that there is still an exceptional 0. There is an exceptional 0, but the distance is the complement. The exceptional 0, which is beta 1, but this time beta 1 is, the earlier beta 1 was greater than or equal to, so this time beta 1 is less than 1 minus c by alpha 1 log qt. Okay. And this time what is going to happen, so it's this term, yeah, x to the power beta 1 by beta 1. So now x to the power beta 1 by beta 1. So this is what you have to bound. This is going to be less than x exponential minus c log x alpha log t. So what remains to do now is to choose your sigma t, and yeah, and then it's done. Okay, so choose the parameters suitably. Yeah. And then you get this theorem. Okay. So now, of course, there's a proof and all that, but is this a very good theorem according to you? I mean, not that is it a good theorem. Of course, it's a good theorem, but is this result strong? Is this result, what's weak about this result? What's weak about this result is that these are not uniform. You have a dependence on beta 1. Yeah? And if you want to remove the beta 1, if you want to get a result where there is no dependence, want to get an uniform result, this becomes a bad result. Bad result in the sense, a result where the Q, you remember here in this theorem, Q was not so bad, but it really gets worse, and that's what we will show you. Okay, so so the moral of the story is that beta 1, so remark, it's a remark I want to make. It's not because I call it a remark that it becomes a trivial remark. Okay, it's just to distinguish it from a theorem that I call it a remark. So the point we should realize is that the term containing beta 1 yeah, is the main difficulty. Okay, to get any good universal upper bound. Yeah. That it would be good as well as universal. Upper bound. All right. So, yes. It's this one. This is where your when would you have the exceptional zero and when would you not have it? That's the point that is coming from this Q. Okay, you cannot have it for all Q because you might come across this. Okay, so now this is a result for an explicit formula. We have not yet done psi x qa. So that's not very difficult. This is called Page's theorem. I don't know where Page was from. I don't quite know. I think he somehow got overshadowed by Landau. So as a corollary of this theorem, oh, not white. Okay, known as Page's result, I mean proved by him. So psi, now instead of this x chi, I have x with q and a given. This is equal to either x by phi of q plus big O x expo x the exp of minus c1 square root of log x if there is no exceptional 0 so if there is no exceptional 0, okay, or it is equal to a term containing exceptional zeros, and this time you're going to still have x by phi q, first main term x by phi q, and then a second, what should be a main term. So this is chi1 a x to the power beta 1 phi q to the beta 1 plus big O x exponential minus c1 square root of log x. Okay. Okay. Here, if beta 1 is the exceptional 0, and chi1, this chi1 is the exceptional character, which gives beta 1. Okay. So this I will leave as an exercise which we can do in the afternoon, okay? So however, we can discuss the question. Yeah. So this one, you see, first part, okay, the pink part, there's no problem. The second part, when beta 1 is an exceptional 0 and chi1 is the exceptional character. Now, you want this one, this term containing the beta 1, you want this to be really a main term. For it to be really a main term, it has to be bigger than the error term. if the main term becomes smaller than the error term, then the error term is not an error term. So it should neither become smaller than the error term or not even equal to the error term. Okay, that's what creates the problem of why I said that having an exceptional zero makes the choice of the range of Q bad. Okay, so when does this become larger? The question is, when does this become the second main term? We'll do the proof. It's not difficult. We can do it in the afternoon. So when does the second main term, the first main term is okay. When does the second main term become larger than the error term? That maybe answers your question about why we cannot allow all Q. So the second main term becomes larger if X is the C1. You remember this, the C1 that we got from the error of the zero-free region. So some remarks, okay? Can you tell me when it becomes larger? So on one side, I have powers of x here, and this is x exponential minus C1. So this will happen when x is less than exponential C1 square by 1 minus beta 1 square. Okay. So you have to take beta 1 to be small. Okay. So one way of going around the problem may be to use Eagle's theorem, which we studied yesterday. We said that, and that would be good, but it would also be bad. Why? Why would it be good? It would be good, you can imagine, because I can control my the existence of the place where the C1 should, with the beta 1 should come. But why do I say that it will also be bad? What would be bad about using the Ziegel's theorem? We talked about it yesterday. What's inconvenient in the Ziegel's theorem? Ineffectivity. Yeah, it's that it is not effective, and therefore what you will gain on one side, you will lose on the other. Okay. So so we continue. We make some more remarks. If we use an universal upper bound, then what happens? some constant over q to the power half log square q bound beta 1 less than this. Then you have a t, you remember? There is a t in this story where the contour integration is taking place. The term t, just let's call it the term. Then the term containing beta 1, okay, in this expression, there's a term containing beta 1, say S. What happens to it? This is my term containing S, and this S is now bounded by, okay, this S is now bounded by, it's less than x by phi q exponential, and here is this my minus C3 log of x. That's the one, q to the power half log squared q. All right. Now, this one you want it to be big enough, okay? So you need the condition. As I said, you don't want your second main term to be, you want your second main term to be not big so that this is really an error term, okay? It really has to, you want it to be an error term when you say that. You can always write an error term, but it may not be an error term, okay? An error term makes sense only if it is smaller than the main terms. We can always write an error term. Nobody stops you from writing an error term. Is it really an error term? That's the question, yeah. And so that's what you want to control. Is it an error term? So to make this, so this one you want it to be large enough. What should you do then? What is the condition that you need? Q should be less than or equal to log x to the power 1 minus delta for a fixed positive delta. Now that is bad. I mean, to make q less than log x to the power 1 minus delta, no one can say that that's a good bound. Yeah, it's a big constraint. Okay, so the theorem as it stands here has this big constraint. Okay, the second term, yeah. What is the question? As it is written, it's correct. You just want it to become bigger than the error term. Yeah. So this will happen if yeah. It's negative, right? So yeah, this is minus. So if I write it as a negative, then the other way it becomes positive. what I'm writing here is that is only chi1a x to the power beta 1, etc. All right. So this one, when you write it as negative, if this one is smaller, then as the negative, the other one is bigger. If a is less, you have a is less than b, then minus a is larger than minus b. So this is bigger, and then when it is bigger, q is less than log x to the power 1 minus delta. Okay. So this is a constraint, okay? This is not so good. Okay. I mean, you would like it to be, you would like more Q to be included. Okay. So can we have a few minutes of break? Then I will tell you about the use of the Ziegel theorem. Okay. So what will happen when the Ziegel theorem is used is that you will see what will happen. Say 5 minutes, okay? Yeah. নাকি জল খেতে পাওয়া যায় কোথাও আছে কিন্তু এটা তো আপনার মানে আপনি কোথা থেকে খাবেন আমি যদি সবটা খেয়ে ফেলি আমিও ভুলে গেছি এখানে না খুব সুন্দর মাটির বোতল পাওয়া যায় দেখেছো হ্যাঁ কল্যাণীতে আমি আজকে বিকেলে যাবো কল্যাণীতে দেখতে ওটা পাওয়া যায় কিনা আচ্ছা ঠিক আছে তুমি তো এত ছোট তাই আমি ভাবছি তুমি পিঙ্ক ফ্লয়েডের কি করে ফ্যান হলে তো অনেকদিন আগে ও এটা তো লিকুইড হয়ে যাবে এটা আমার ভিতরে ঢুকে যাবে হ্যাঁ 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 ও ওকে 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 তুমি একটু বড় করতে চাইছো তো না এরর টার্মে তো তোমার কোনো এরর টার্মে তো তোমার কোনো বিটা নেই যায় হ্যাঁ হ্যাঁ তাই একটা মেইন এক্স বাই ফাই কিউ তো আছে হ্যাঁ ওকে 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 হ্যাঁ তুমি ঠিক বলেছো তুমি হ্যাঁ, যাতে প্রথম মেইন টার্মটা মেইন টার্ম থেকে যায়। হ্যাঁ, ঠিক বলেছো তুমি, ঠিকই বলেছো। হ্যাঁ, তুমি ঠিক বলেছো কথাটা, এটা ঠিক বলেছো। হ্যাঁ, কারণ পরে আমরা যখন জিগেল ওয়ালফিসে নেব তখন একটাই এরর টার্ম থাকবে। হ্যাঁ, এটা একটু মিক্সচার আছে দুটো বইয়ের। ডেভেনপোর্টে ডেভেনপোর্টে সুন্দর করে করা, মানে ডেভেনপোর্টটা পড়লে মনে হবে খুব সহজ সবকিছু, কিন্তু আসলে অত সহজ না, মানে লেখার ধরনটা আর কি। ডেভেনপোর্ট মনে হয় যে সবটা খুব সহজ, মানে গল্প বলার মতো করে লেখা। হ্যাঁ, আর ছোট্ট একটা বই এইটুকুনি। আর মন্টগোমেরি ফোনটা হচ্ছে খুব মোটাসোটা, আর অনেক ডিটেল দেওয়া আছে ওর মধ্যে, মানে কোনো কনস্ট্যান্ট ওরম ছেড়ে দেয় না আর কি ওরা ওটাকে, তারপরে ওটাকে কতটা এক্সপ্লিসিট করে লেখা যায় সবকিছু লেখে, সেটা তখন একটু ঘুম পাবে না অত সহজে ওটা নিয়ে। কিন্তু ডেভেনপোর্ট নিয়ে বেশ তারপরে তোমার ডিটেল গুলো দেখতে হবে যে আর কি কি করে কি কারণে বলছে আর কি কথাগুলো। কিন্তু একটা ঘটনা হচ্ছে যে ডেভেনপোর্টের যে ইয়েটা, ইন্ট্রোডাকশনটা, না মানে নতুন এডিশন যেটা বেরিয়েছে সেটা কিন্তু মন্টগোমেরি লিখেছে। কাজী 20 চ্যাপ্টার 23 থেকে 29 ওই বইটার যেটা শেষ 6 চ্যাপ্টার, সেটা মন্টগোমেরির লেখা। যে রিভাইজড বাই, থার্ড এডিশন যেটা, সেটা রিভাইজড বাই মন্টগোমেরি। শুরু করবো? আচ্ছা, আমাদের সব এই যে আমাদের কথাবার্তাই সবই কি রেকর্ডেড হয়ে যায়? আচ্ছা, জল খাওয়া টাওয়া সব রেকর্ডেড হয়ে যায়? আচ্ছা। So when we wrote the first theorem, there was a constant, you remember, and we called that constant C1. So you might have wondered why we began the course calling it, giving it a subscript. The reason is that we will use it. I wanted it to be kept separately so that we can use it and say that that is the same. I don't know whether we named the theorem anything. Did we name the theorem in the explicit formula? Okay. In the explicit formula, there is a C1. Yeah. And that's the same one which we will now use in this new result, okay, where we will assume Ziegel's theorem, okay. So we recall, first of all, that beta 1, there exists 1 minus c epsilon and q to the power epsilon, yeah. There exists, for every epsilon, there exists a constant that depends on epsilon, such that beta is less than 1 minus c epsilon by q epsilon. This is Ziegel's theorem from 1930. All right. And now we will show a corollary, not of Ziegel's theorem. I mean, it uses this, but it comes from the explicit formula. Okay. So corollary of the explicit formula is which I should have given a name to it. You can maybe give it a name. It was the first thing we did today, okay, of the explicit formula. You could call it, you could give it a name to that theorem, okay. So, if I take any positive A, then there is some x0 which depends on A such that Q here is less than equal to log x to the power A. All right. Then that's a reformulation. Then the explicit formula psi x chi is equal to E0 of chi times x plus big O of x exponential minus C1 square root of log x. Okay. For what? For all x greater than or equal to x0. Okay. So let's see how we prove this. Proof. If chi is quadratic, and LS chi has an exceptional zero, which I call beta 1, then what happens? X to the power beta 1 is equal to x exponential minus 1 minus beta 1 log of x. There are too many. Which is less than or equal to x. I wanted to say something. C1, where is my, this C1 is the constant in the explicit formula. All right. So so now I can use the fact that this can be bounded by minus C epsilon Ziegel q to the power minus epsilon log of x. Yeah. So this is Ziegel. And this, let's take another color. Okay. However, q is less than or equal to log x power a. Okay. So use that. If q is bounded by log x power a, then this one is bounded by here. This is bounded by so from here I come, less than or equal to x exponential minus c epsilon log x to the power 1 minus a epsilon, which is less than or equal to x exponential minus c. This c is the c of this c, okay? Not the same, not necessarily the same one that comes from the explicit formula. Square root of log x okay. So for every epsilon, I can do this. So I take epsilon to be equal to 1 by 2a, okay, and x to be greater than or equal to x0, which is the x of C1 and C0, C epsilon to the power to some power. Okay, and then we are done. Okay. So I want to Now state, now I want to state a quantitative form of the prime number theorem. So you know that qualitatively we know that there are infinitely many, and quantitatively what can we say? So for this, here I will state it as with the von Mongold, and then we can go back to the pi. Okay, so here is the Ziegel-Wolfis theorem. Okay, so again I will let C1 be the constant in the explicit formula. Okay, we will fix a positive, that A that we had. Okay, where is it? Here. Let us fix an A. All right. So now you let Q to be less than or equal to, here, Q is less than equal to log x power A. A and Q are co-prime. Then I can state the Ziegel-Wolfis theorem now, which is not in terms of x pi, but in terms of x, q, and a. So psi, okay, we'll state it here because on this side. xqa. You remember the main term. This is x by phi q. And then I take in everything into my error term. So what is it? X, I get an x. I get an exponential of what? Of that C1, remember? The C1, there's a C1 and there's a square root of log x. And this depends on the A that we fix. All right? So that's the Ziegel-Wolfis theorem. And so now the range is Q is less than equal to log x to the power capital A. However, there is the fact that we have lost the effectiveness. Yeah, what we have gained for the range but lost in effectiveness. Yeah, so the choice is yours. Yeah, yeah. Yeah. Ye- This is with the XQA, and the other one was with X chi. That was for the 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 corollary.
Okay, depending on the character.
That depends on the character. Yeah. And this is when it is like when we first had the explicit formula, how we got an asymptotic for.
Okay, that was for quadratic character.
Yes. Okay. And this is XQA. So so the universal bound that we if you want an universal bound, then, well, you lose in terms of the effectiveness of the constants. Yeah. So now from here, if you have the Ziegel-Wallis theorem, you can also prove the prime number theorem. So instead of writing it, so theorem, this is the prime number theorem. I mean, that's what we were supposed to find, yeah? So this is the prime number theorem in arithmetic progression. Which means now we will not state the result in terms of psi, but in terms of pi. Yeah, just as that's how you did it for the prime number theorem, the usual prime number theorem also. I think the prime number theorem is something that everybody knows, but the prime number theorem in arithmetic progression is maybe something that not everybody knows. Everybody means everybody on the streets has heard of the prime number theorem, right? Do you know anyone who doesn't know the prime number theorem? There is no such person. Everyone knows the prime number theorem. But not everyone knows the prime number theorem in arithmetic progression. For that, you're special people who have seen the proof and you know it. Yeah. So again, we will have the same conditions. So I'll write it out nicely. Again, I will take C1 to be the constant in the explicit formula, and I will take A and Q to be co-prime to make my definitions. And then so now I want to write, I gave a definition right in the first, remember that? Pi of x q a, it's equal to the number of primes that are less than x. P is congruent to a modulo q. So this has not been smoothed out by lambda of n. Okay. Then pi of x qa, this is equal to the logarithmic integral x divided by the normalizing phi q plus big O exponential minus C1 square root of log x. This with the same C1. And when there is, this is one case. This is the case when there is no Ziegel zero. All right. And if there is a Siegel zero, Siegel zero, which is beta 1, and of course, then pi, and there is no Siegel zero modulus q, okay? Otherwise, it is equal to the logarithmic integral by phi q always, and then comes a term which will involve the betas. So this is chi1a. Chi1 is the exceptional character. The logarithmic integral x to the power beta 1 and phi q plus, I get the big O again, exponential minus c1 square root of log x if beta 1 is an exceptional 0 and chi1 the exceptional character. So maybe this is how you had seen your, this is how the, so you see if q becomes equal to 1, then do you recover the prime number theorem? Yeah, you recover the prime number theorem for at least, I mean, it's one way of writing the prime number theorem. This is the way that de la Vallée-Poussin, I think he wrote it in this way. Because you know that prime number theorem was not proved jointly by Hadamard and de la Vallée-Poussin, but separately. They were both working on that, or a lot of people were working on that. But we always say prime number theorem was proved by de la Vallée-Poussin and Hadamard, but they didn't do it together. So there is if you go back to and read the real papers, those papers, you will see that they are stated in not necessarily exactly the same manner. So the way that when q is equal to 1, this you get back the statement of so this is a generalization of the prime number theorem as stated by de la Vallée-Poussin. Okay, Hadamard did not state it like that. So then he wrote it with exponential. This, and then the second case does not come, right? Because of course, when you have zeta functions, you don't have Siegel zeros. Okay. So do you know how to reach from psi to pi? So how do you go from psi to pi? It's the same way as you did for zeta. You want to imitate the proof? How do you go from, that is the, we wrote the result for psi and then we wrote the result for pi, but how do you come from psi to pi? That is, how do you come from von Mongold to the counting function? Yeah, you must have seen that. You did that with them. Yeah? So how do you do that? You don't have your So for that, okay, so you can take a third function, that is you have pi, you have psi, and you have theta. Yeah. So so let theta, it's x qn of a. This is equal to, instead of lambda n, we take it to be sum of log of p. Okay, and p is congruent to p is less than equal to x, and you have a congruence condition a mod q. Yeah, p is congruent to a mod q. So you can integrate the Siegel-Wolfis theorem by parts, and you imitate the proof of, so pi of x, how do you come from psi to pi? So you do this via theta. Okay, so maybe you can do that yourself. So you can express pi in terms of theta. So if you do that, pi of x qa, how would you write this in terms of theta? So theta is, this takes the sum of log of p. So you have a log p, which is, you have a 1 by log p. So we won't call it p, we'll call it u. And then you take the derivative u q of a, and you integrate this. Yeah. So, and you get back pi. So what do you get as the first term if you do that? What comes out as the first term? There are you imitate the proof for the prime number theorem. Okay. So the main term comes out as the logarithmic integral Lix divided by phi of q. Okay. And then you have another integral, which is 1 by log u d theta u q a minus u by phi q. And this goes between 2 and x. Okay. Now integrate by part. If I integrate by parts, then this one, theta u q a upon log u take it between 2 minus and x, and you'll get back your prime number theorem. Okay? You can finish it, the last line. Take a product of two functions and integrate it. That is something usually not complicated, can be done. Yeah, is there something different with the prime number theorem here? No, nothing is different. It's exactly the same proof. You can copy and paste. So in the afternoon, we will do some exercises. As I told you that the problem with this is that you don't get the good range. Either you don't get the good range or you don't get a good effective constants. So because of the presence of zero zeros. So either one or the other is a problem. So if we take some conditional results, that is, if we assume, for example, the generalized Riemann hypothesis, then things will become nicer. And we can do a little bit of that as exercises this afternoon. These will be generalized. These will be conditional. Um, conditional. Either it can be for the explicit formula, or it can be for the prime number theorem. Okay. And we can do a few such questions in the afternoon. Is that okay? I don't have anything else to say just now.